delay, there are some things I want to say first. So you should have gotten your name badge, and that contains a code for the Wi-Fi in case you don't have Ethereum. We have some stationery here in case you need that and the program. Coffee breaks will be upstairs, and there will be a signpost telling you which is our coffee area, because there's a second conference or second meeting going on, and they will be upstairs there as well. If you haven't paid yet for the dinner and you want to participate, make sure you find Rosanna. She'll be around tomorrow at the same spot over there. And yeah, just make sure you pay the 35 euros. And if you have any dietary requirements, please make sure that it's recorded correctly with her. Check with us. Yeah, of course, you can also always come to either me or Sven, or to Rosanna directly if you have any questions. And now we just start. We have Fernando who will say a few words, and then we start the program.
Thank you. Well, welcome to all of you here. It's a great pleasure to have you. Sorry for the delay. It's my fault because I had to open another conference next door. So that tells you more or less the number of activities we have. We have like 50 to 60 activities every year here. I can see a lot of faces that I know very well, and I can see many of you already know ICTP, but it's my duty to say something about ICTP every time we have an activity, and I think something may be informative to some of you. So, so you know, we have been running for more than 50 years. This ICTP was created by Abdus Salam in 1964. The idea is to have science at the highest possible level, but also to promote science in developing countries. So that's what it's a double mission, and believe it or not, it has been very successful for all these years. So it has been an honor for me to be the director for the last 9 years. I'm finishing a year from now, and so we have been expanding in scope and in activities over the years. And so now we have covered high energy, condensed matter, mathematics, climate change, seismology, and renewable energies, and now quantitative life sciences. In quantitative life sciences, we are just creating a group, and actually last 2 weeks ago, we had a school for 2 weeks precisely on machine learning in quantitative biology. So, so that's always is one of the activities we are moving toward. In what we call quantitative life sciences will include machine learning and artificial intelligence, plus other things on top of just biology in general. So that's the fields. We also have education programs and a new master in medical physics that has been one of the success stories for our ICTP, because we are helping countries to develop the medical physics that they didn't have in the past. So that's something that direct impact to the society. And also we have been expanding in the regions. We have now opened 4 different partner institutes. One in Brazil, probably you have heard, ICTP Cypher, and now 2 that just started. IFER, ICTP East African Institute of Fundamental Research, which is in Rwanda, and the one in China, ICTP AP, Asian Pacific, that just started 3 weeks ago. So you will see in the next few days advertisements for jobs. At least in the one in China, we'll have at least 5 positions in our field, and we are very excited to be developing that direction. That is an institute that it is based in the Chinese Academy of Sciences University in Beijing, with the potential to expand as much as possible, depending on how well we work together. So in that sense, it's important. So hopefully in the next future, we will invite you to activities there, and maybe we can invite you also to apply to positions there, to some of you who are young enough and adventurous enough to apply abroad. And so anyway, so I don't want to take too much of your time, so I'm very keen on this activity. But I know that this is, I would say, is the 3rd or 4th activity in machine learning in the last year or so, which I think it shows that machine learning for string theory I think they were started in Northeastern, and then now there was in Munich and China, and then here. So we have very enthusiastic organizers. I'm in the list of the organizers, but you can see I haven't done that much. So, and I think we can start. I think either you will introduce the next speaker. Okay, well, thank you.
Thank you very much, Fernando. And now we start directly with our first speaker, Jim Halverson.
Sorry, still have 45 till 10:07.
All right, so Jim is our first speaker, and he's from Northeastern and will tell us about complexity of machine learning and the landscape.
All right. Thanks to the organizers for organizing this wonderful conference. It's wonderful to get to go first so that I can tell you about what I'm interested in and then hear all of your wonderful talks. I'm not used to having screens on both sides. This is kind of new, so hopefully I'll navigate that well. So the title of my talk is Complexity of Machine Learning and Landscapes. I am going to speak on recent work with Fabian. Let's see how this works. Laser pointer, good. Recent work with Fabian from September. You might be asking, why is Jim going to talk about complexity at a machine learning workshop? The first answer is a simple one, that I have two collaborators who are talking about our work on machine learning at this meeting. But the more practical one is that as we sort of start to do this more and more, as we start to apply machine learning and data science to string theory, it's really important, I think, to ask what sorts of things can we hope or expect to do in general, which sounds pretty vague when you put it that way. But in fact, there's a field in computer science called computational complexity that is all about sort of the difficulty of computations. And so what I'm going to try to do in this talk is try to put some of the questions that we naturally ask in the context of string theory or in landscapes more generally in the language of computational complexity and see where we get. Okay, so I'm going to organize my talk around a series of 5 questions. The first question is, why should string theorists care about computational complexity? So the punchline, and then I'll make some bullet points, is basically just that difficulties that we run into in landscapes are not only due to the exponentially large sizes that we see in string theory, which, because of the exponentially large size, it takes exponential time to process those examples in our data by nature of their size. The difficulties that we run into are also due to the existence of problems that are fundamentally hard, which take exponential time to solve, not because of their size, but because of their fundamental hardness, because of their complexity. And so because we run into both of these sorts of difficulties, not just large sizes, but exponential time problems that we run into, progress really requires dealing with both of these obstructions. Okay, so complexity more broadly, why should we consider this? I'll define what complexity is for a good chunk of the talk. For now, just think of it as some notion of hardness. Some notion of hardness of a given computation that can be made precise, and we'll get to what that means. But for this slide, it just means hardness. So one reason why you might want to consider it is that we have goals when we're doing some given physical computation, and we often find that we run into bottlenecks. And you might ask, is it because we're just not that good at this? Are we not sophisticated enough in the computations that we're doing? Or is it because there's some sort of fundamental obstruction? And while in some cases we certainly probably could be doing things in a more sophisticated manner, which is part of what this whole program is about, on the other hand, there are problems that are just fundamentally complex, and we can run into such problems. Another reason is that when we consider the physical problems that we care about, it may be that observables that we're interested in are fundamentally computationally hard in a way that trying to understand those observables requires dealing with a hard problem. Famous examples include the Boussel-Pochinski model, cosmological constants in the Boussel-Pochinski model, and in the Arkani-Hamed-Dimopoulos-Kachu model, there's a related CC model. And in both of these cases, it's known that finding small cosmological constants is computationally hard. So this is a case where some observable about the world that we really care about in the context of string theory is finding it requires solving a computationally hard problem. This is a result of Denef and Douglas. On the other hand, you might have some case where in a landscape there's some observable that you really care about. It may not itself be the result of a computationally hard problem, but it may correlate strongly with some other aspect where some other problem where requiring the answer to the problem that you want to know, the critical observables, requires solving some other hard problem just to get at it. Okay. Something that I'm not going to talk much about in this talk, this is an idea that's due to a recent paper by Douglas, Denef, Green, and Zukowski. Another idea that might be a reason that you care about it is if a physical system implicitly solves a problem, then hardness results can affect its dynamics. So in the context of protein folding, this is well known. We'll talk a little bit about protein folding in this talk. But this paper here by Denef, Douglas, Green, and Zukowski has proposed this as a new way to think about measures in the landscape, that some of the ways that we think about measures and dynamics might be influenced by computational complexity. That is a fascinating idea. I'm going to stick to other things in this talk, but I highly recommend that you look at this work. And finally, another thing that I'd like to mention that is not something I'm going to talk about is undecidability. Undecidability is related to complexity. There's a type of problem that we'll discuss called a decision problem, and it turns out that any decision problem can be turned into a DayaFantine equation and trying to find solutions to a DayaFantine equation, but there are results from number theory, a theorem due to Matijasevich. It is a negative result to Hilbert's 10th problem that basically it tells you that there is no algorithm that can universally solve DayaFantine equations, and therefore, because that's the case and because decision problems arise so regularly in string theory, you might worry that there's just, as you might expect, but it can be made formal, there's just no algorithm by which you're going to be able to peruse the landscape systematically because of this issue of DayaFantine undecidability. Okay, so these are some of the reasons why we might consider complexity. The most practical one is just that we run into computational bottlenecks, and we'd like to understand why that is and what sorts of obstructions are in our way. So the outline is 5 questions. Why should string theorists care about computational complexity? We've just gone through that one. Next up is what is computational complexity? After that, we'll ask, given that we now know about computational complexity, what is the complexity of vacua in landscapes? What is complexity of vacua in the string landscape? Those are 2 different questions, and we'll talk about the differences between them. And what are potential complexity loopholes, and what does it mean for applying machine learning or AI to various landscape problems? So this is what we'll be attacking. So up first, what is computational complexity? I was giving a talk on this subject just on Friday, happily. And as I was going through this part of the talk, I felt that it would be good to tell you where the next few slides are going in case you're not as familiar with this subject. First, what we'll do is we'll introduce the notion of a problem. A problem is the subject of computational complexity. What is the complexity of a given problem? This leads to a notion of P versus NP that you've probably heard of. That's the notion of a complexity class, asking the question whether some problems are fundamentally harder than others. Then we'll talk about a notion of a polytime reduction. A polytime reduction is basically a way of relating 2 problems to one another in polynomial time, such that you can say, if I can solve this problem, then I can solve this other problem in polynomial time as well. This will lead to a notion of the hardest problems in NP. We'll then talk about the difference between optimization problems and decision problems, and then I'll give you an example. So that's the flow of the next bunch of slides. That's where we're going. So a problem is the following. A problem, F, maps instances in some set I to outputs in subset B. So it's a simple definition. There's lots of different examples. And you can think of casting many different things that we think about in this framework. A decision problem is the specific case where the output set B is yes or no. Does this particular instanton zero mode exist for this divisor or not? Yes or no, for instance, but there's many other examples. So let me give you an example of a decision problem. So first, a clique of an undirected graph is a set of vertices that are all connected to one another. And there's an associated problem called clique. Problems in complexity are often written in all capital letters, so I'll try to stick to that convention. The problem clique is given an undirected graph G and an integer n in Z, does G have an n clique? An n clique is a clique where n vertices are all connected to one another. So in this case, the instance set is S, the set of undirected graphs, times Z, the integer that you're inputting. And the output is just yes or no, whether for that graph there is a clique, an n clique or not. Okay. We say that an algorithm computes the problem F if it always returns an output. So it's something that is going to halt. That's what we want. We want an algorithm that's going to finish on the problem that we care about. And finally, a polynomial time algorithm or a polytime algorithm returns an output in a time bounded by a polynomial in the input size. And if we don't have an algorithm of that type, if we don't have a polynomial time algorithm, we'll say that we have an exponential time algorithm. Okay? So for instance, if you wanted to factor an integer into its primes, this is a famous problem in complexity, it's behind cryptography, the integer has n digits. And you might imagine that the factoring problem, how long it takes to factor that integer is going to be a function of n. And it's a natural question to ask whether or not there is a polynomial time algorithm in the number of digits to factorize that integer. Okay. Let's talk about P versus NP. Now that we know what a problem is, and we know what a decision problem is, and we know the sorts of things that we'd like to ask for a given problem, is there a polynomial time algorithm that computes the problem? It's natural to ask, are some classes of problems fundamentally harder than other classes of problems? P is the class of problems with polynomial time, polytime solution algorithms. A trivial example is multiplication. Given two numbers, I can multiply them very quickly. But a non-trivial example, because sometimes people like to know, is there something that you thought might not have been in P, but actually is in P? There was this famous paper from, I believe, the early 2000s called Primes is in P. And the non-trivial example of something in P is primes. So primes is the problem given an integer, is it prime or not, yes or no? So it turns out that there is a polynomial time algorithm for solving that. So primes is a non-trivial example of a problem that's in P. On the other hand, P, which is about polytime solution algorithms, you can ask about the class of problems with polytime verifiers. That's known as NP. So a verifier means that if I hand you a proposed solution to the problem, you can verify in polynomial time that yes, indeed, it is a solution. So NP contains P. So all problems that are in P are also in NP. But there's a natural question of whether or not it is fundamentally different to solve a problem or check a proposed solution. Is P equal to NP or not? For an example of NP, think of a Sudoku puzzle, for instance. We know that solving Sudoku is relatively hard, but if someone hands you a proposed solution to a Sudoku puzzle, it's actually very quick to check whether or not it's a solution. So Sudoku is a case where there is a polytime verifier. If it is a solution, if you're handed a proposed solution, you can verify very, very quickly whether it is or not. But if I hand you a puzzle that is meant to be solved, that seems like a much harder thing. Okay. So the question is P versus NP. Is solving problems, that is problems in P, is solving problems as hard as verifying proposed solutions? That's the question of whether P is equal to NP or not. So solving problems is what P is about in polynomial time. Verifying proposed solutions is what NP is about. And so there's this question of whether they're the same thing. So is P equal to NP? This is one of the Clay Millennium problems. It is unsolved. It's an open problem. But the consensus in computer science is that P is not equal to NP. And I gave a talk on some of this work at the Simon Center in August, it was. And when I said this, when I posed this question, what do you think, is P equal to NP or not, someone laughed because it just, when you phrase it this way, is solving problems as hard as verifying proposed solutions, it seems so obvious that those are fundamentally different things. But it is, in fact, an open question. So what we're going to be doing in this talk is working under the assumption that P is, in fact, not equal to NP. But please keep in mind that this is an open problem. Okay. So if P is not equal to NP, you might ask, is there a notion of the hardest problems in NP? Are some problems in NP at least as hard as any other problem in NP? So to talk about the hardest problems in NP, I need to give you a way to relate two problems to one another. And the way to do that is using something called a polynomial time reduction. So if I hand you two problems, F, which maps I to yes, no, and G, which maps I prime to yes, no, we say that there's a polytime reduction from F to G if there's a polytime algorithm, little f, that maps instances of in I to other instances of the other problem in I prime, such that f of x is yes if and only if G of little f of x is yes. What this basically means is that if we have a reduction from f to G and I can solve G, then I can also solve f in polynomial time by this correspondence, by basically using the solution to G and then relating it to the instance of f via the polynomial time reduction. Okay. So reduction gives us a way to relate problems to one another, and in particular, it gives us a way to solve, if you can solve one problem, then you can solve the other one as well. So in particular, if there is a polytime algorithm for G, there is also a polytime algorithm for f via the reduction. Okay, now that we have this notion of the relation between problems, we can talk about the hardest NP problems. A problem G is NP hard if there exists a polytime reduction to G for every problem in NP. Practically, what this means is the following. If you can solve G, you can solve every problem in NP. The little Venn diagram you should have is here. We are working under the idea that P is in fact not equal to NP. The Venn diagrams will change if they're equal, keeping in mind that that's an open problem. But P here is sitting inside of NP. Problems that are NP hard, what this means is that any problem in NP can be mapped to the NP hard problem in polynomial time. So if you can solve any problem in here via this map, you can solve any problem in NP in polynomial time. So if there's a polynomial time algorithm for anything in here, there's a polynomial time algorithm for everything in here. So in short, what that means is that if you find a single polynomial time algorithm for any problem in NP hard, you can effectively solve every problem in NP in polynomial time, and that would prove that P is equal to NP. Okay. Right, so therefore, taking the contrapositive, if P is not equal to NP, there is no polynomial time algorithm for anything in NP hard, and therefore the problem takes exponential time. Henceforth, when I refer to a hard problem, what I will mean is a problem that takes exponential time if P is not equal to NP. Okay. Yes?
The way you've been describing things, it's always understood exactly what the size of the input is. For example, the size of a matrix or the number of digits or something.
Exactly.
Is there always duality invariant in physics problems?
That's a good question. Yeah, I don't know. I haven't thought about that specific idea. One of the things we'll talk about at the end is potential loopholes, ways to get around these sorts of issues. And if you ever had a duality that effectively shrank the n, if two problems are dual and you have n and n prime, you might get gains. Another way to say that is that the effective number of degrees of freedom that you had wasn't actually n, it was really n prime in the other duality frame. And that's one of the things we'll talk about at the end. But specifically with respect to string duality, I haven't thought that much about it. It's a good question to ask.
There's one example in the paper, I don't know whether you will talk about it, it's finding for elliptically fibered Cavaliers, finding the devices.
No.
There are examples where, for example, if the Cavalier is elliptically fibered, something is very easy to compute. To take the mirror dual, which might not be elliptically fibered, it's very hard. So in this sense, it's not invariant.
Yeah. Yeah, but one of the fundamental questions is, after we set up all of this framework for thinking about hard problems, how do we potentially get around these problems, right? And duality is potentially one of them. Okay, so an NP complete problem is one that's NP and NP hard. So it's the intersection of NP and NP hard. Here it is, NP complete. And examples are subset sum and knapsack. Subset sum is something that is very simple to state. If I hand you a set of integers, is there a subset that sums to 0, yes or no? Very, very simple problem. So simple that it sounds silly, but in fact, subset sum can be mapped onto cosmological constant problems, for instance, where solving the cosmological constant problem can be rephrased in terms of solving some particular subset sum problem. And similarly for knapsack. Knapsack is the problem that you're going hiking and you have a pack that has a maximal amount of weight that it can carry, and there's a whole bunch of items that you want to put into that pack, n possible items that you might put into that pack. Each of them has a weight and a cost. And when you're trying to figure out what to take hiking, you're trying to maximize the amount of value that you can put in your pack, subject to the constraint that you can only carry so much. Right? So this is an NP-complete problem. It's called knapsack. So it's true that some NP-complete problems can have instances in P. So being NP-complete means that there are instances that take exponential time if P is not equal to NP. But you can have special instances of a problem that in fact are polynomial time, even if the generic problem is not, and provably not. Right? And the physics backdrop that I always have in my mind is that cosmological constant problems that we know and care about in string theory, Bussel-Paczynski and Arkani, Hamed, Dimopoulos, Kotru, are in fact NP-complete problems. Okay. Optimization versus decision. Technically, we've been talking about yes-no problems. Decision problems, those are yes-no problems. Complexity classes are defined with respect to these decision problems, these problems with yes or no answers. But that's not the type of problem we're always after. Sometimes we're after a problem that we might call an optimization problem. Given some function h of x, find a local or global optimum of h of x. But to such an optimization problem, you can always associate a decision problem. Is a given point x star a local or global optimum of h of x, yes or no? And in this sense, you can sort of see that optimization problems O are at least as hard as associated decision problems D, because if you solve this problem here, the optimization problem, you can implicitly solve D. This is finding the global optimum is in a sense harder than trying to answer the decision problem. So the reason why I mention this is that a lot of this talk is really secretly about optimization problems, but there is this relationship between optimization problems and decision problems that's very important. Okay, so a classic optimization problem is protein folding. I've put some of the literature up here that's relevant. Protein folding is a complex system that's analogous to the string landscape. This is something that the Denef-Douglas paper from 2006 talks about for maybe a page or two. And the basic question is, given some protein, some chain of amino acids, how is it that you go from the input sequence of the chain of amino acids to what the three-dimensional folded state is? This is something that's been arising a little bit recently in the news due to progress by DeepMind on this problem. But the analogy that is interesting to draw is to think of this problem as analogous to the string landscape. And in fact, as many of you know, in the literature on this subject, they actually call it the energy landscape of protein folding. So protein folding, finding the global energy minimum, going from this to this, is an NP-complete problem. This is a result of Unger and Molt from 1993. And this can affect dynamics. So in particular, if you create a random stretched protein in the lab and you let go, you see that, in fact, the folding time is exponential in the length of the protein, in the number of amino acids appearing in it. On the other hand, it's true that the proteins that are in you and me fold quickly. And the upshot is that the worst case instances of this problem are hard. The problems if you just create a random protein in the lab are hard, but the ones that are in us, the proteins that are in us fold quickly because there's a special evolutionary pressure that gives rise to these better instances. So there's various literature that discusses this. I have been reading some of it recently. Peter Wolinus visited Northeastern a few weeks ago and sent me some of those papers, so if you're interested, I can send you some of them as well. Okay, so I'm not going to have too much to say about dynamics, but there sort of is this question that some people are interested in, beginning with the work of Denef and Douglas, but I'm also interested in it, which is, can we use analogies from other complex systems for how computational complexity governs dynamics to think about how it actually governs the dynamics in our computationally complex problem, the string landscape? Okay, so we're out of the intro section, and we're on to the problem, which is, what is the complexity of vacua in landscapes? So the question is this: given a scalar potential v of phi, is it hard to find stable vacua, metastable vacua, or near vacua? A comment is just that training neural nets is, in fact, effectively the same problem. And some of the complexity results carry over. There's some subtleties regarding loopholes that we'll discuss at the end, but some of them carry over. But this is our question. Given a V of phi, can you actually find vacua? Is that hard? And again, I'll say it one last time. Hard means exponential time if p is not equal to np. So here's how we're going to frame the problem. Finding vacua is the problem of finding a critical point, and then given a critical point, determining whether or not it is in fact a local minimum. So that begs the question, is it hard to find a critical point? And then, given a critical point, is it hard to determine whether it's a local minimum? And is it hard to determine whether it's a global minimum? On the other hand, you might say, maybe we tunnel to the side of a hill and we begin inflation, and that point is a near vacuum, if you'd like. And is it hard to find such a near vacuum? So we'll start with all our critical points hard. So the way that we're going to do this is we're going to take a polynomial v of phi. Of course, we could have much worse case instances, and we do in string theory. But given a polynomial v of phi, we're going to ask the problem crit points. Crit points is the problem of finding critical points of v of phi. And in particular, we know from how we do this, we take derivatives, which is going to give us another set of polynomials. It's going to give us a set of polynomials. And then we're asking about roots of that. That's what crit points is. So solving crit points requires finding roots of a non-trivial system of polynomials. We'll call that problem polyroots. And the claim is that polyroots is NPhard. So this is the one super concrete derivation that I'm going to give you in this talk, because we need to see at least one. And we're going to need a problem, to show this, we're going to need a problem called SAT. SAT's the following problem. Given a CNF formula, rho is rho satisfiable. But I haven't defined any of those things, so let me give them to you quickly here. A literal of a Boolean variable is the variable x, or its negative, not x. Not will be written like this, so this is not x10. A clause is an or of literals, so x1 or x3 or not x10 is how this reads.
What will CNF?
Oh, it stands for like conjunctive normal form or something like that. What is it? Is it? That is not what I've seen in the, maybe I'm not sure. The CNF part will not be the critical thing here. All I need is what's on the slide. Yeah, I think it's not, I think it's conjunctive, but I'm not sure. Right, so a literal of Boolean variables is the variable x or not x. A clause is an or of literals, for example, x1 or x3 or not x10. We can take an and of clauses, x1 and x2 or not x1 and not x1 or not x3. And this is what we will call a CNF formula. It's satisfiable if and only, we say that it's satisfiable if and only if there is an assignment of values to the Boolean variables such that rho evaluates to yes. Or 1. The Cook-Levin theorem is a famous theorem in any computational complexity textbook. And what they show is that SAT, this simple problem, is NP complete. So this is the problem that we have in the backdrop, SAT, and we're going to relate it to polyroots. And the way that we want to relate it to polyroots is via a reduction. So polyroots, to remind you, is given a system of polynomial equations, is there a non-trivial root? We want a polynomial time reduction from SAT to polyroots, which means that for each instance of SAT, we have to construct an instance of polyroots such that non-trivial roots exist if and only if the SAT problem is satisfiable. So here's how we'll do it. We'll form a system S of polynomial equations. For each Boolean variable xi in the SAT problem, we're going to add this polynomial xi1 minus xi to S. We'll associate a particular polynomial p of L to each literal via, in the case that L is the literal, we'll put in 1 minus x. In the case that it's not the literal, not x, we'll put in x. And then given a clause that's formed of literals in this way, we can associate another polynomial p of c by going through all of the clauses and taking the product of these p of l's. And for each clause c in the CNF formula, we'll add this p twiddle of c to s. So there's two types of polynomials in S. For every clause, there's a p twiddle of c, and then for every Boolean variable, there's an xi1 minus xi. This is what is, finding roots, of course, requires that xi is 1 or minus 1, which is why these are in there. So it's a fact that this system of polynomials S has a non-trivial root if and only if the CNF formula is satisfiable. And because of that, polyroots is NP-hard. Now polyroots isn't exactly the problem that we care about. We care about critical points. and we want to reduce a hard polyroots instance with this system of polynomials to critical points where we are interested in the critical points of this scalar potential here. It turns out that H here is supposed to be V of phi. V of phi has critical points if and only if polyroots, the polyroots instance has a solution. And therefore, via reduction from SAT to polyroots to crit points is NPhard. So finding a critical point of a polynomial equation, V of phi, is NPhard. No, so the reduction only maps onto certain instances. You could try to map onto as general of an instance as possible, and this is exactly related to this caveat that when we talk about computational complexity, it's about the worst case instance. So there are instances of this problem that are exactly equivalent to solving a SAT instance. I can form a crit points instance for every SAT instance. But there could be cases that in fact take polynomial time, and these could be things that are missed by this mapping, for instance. Yeah. So it's not one-to-one. It maps onto, potentially onto a subset. Metastable vacuum is the following problem. Find a local minimum of V of phi such that it's in this box. These are called box constraints in the literature. This is one of the main things that our paper added to the problem. The basic idea is that we want to impose box constraints so that we encode the fact that the effective field theory that we care about has a regime of validity. You wouldn't want to consider vacua with scalar field values much above the cutoff, for instance. So the cutoffs in our scalar field theories are putting our theory in some box. There's a decision version of the problem. Is a critical point phi star a local minimum? This is something called co-NPhard, but this basically, if p is not equal to np, just translate this for now as exponential time. It's true. This required a modification of something called local quadratic programming to the quartic case. The proof is in the extra slides. And that put the difficult problem in the interior of the box for the effective field theory, so we're not considering critical points that are right on the boundary of validity. We want to have cases that we really trust. But it turns out that this is actually only difficult for the case of a semi-positive definite Hessian, a positive semi-definite Hessian. So if your Hessian is positive definite, if you know it's a critical point and the Hessian is positive definite, you just do the order n cubed diagonalization process to determine if in fact it has all positive eigenvalues. You can determine that in order n cubed time. Okay? So it's hard only for the case of positive semi-definite Hessian. And here's some comments on the proof. The optimization version is in fact something different. Find a local minimum. That is, first you must find a critical point, which is NP-hard, and then given that critical point, you have to solve this decision problem, which in the case of positive semi-definite Hessian of that critical point is co-NP-hard. So you sort of have stacked up hard problems. And then there's a comment about something called strict saddle points, which is interesting, but I'll leave it there. Stable vacua is asking the problem about a global minimum of V of phi rather than a local minimum. And because we know that the local minimum problem is hard, we immediately determined that the global minimum problem is hard because the local minimum problem is already hard itself. So difficulties of global minimization are well known, for example, in quadratic programming or protein folding. In fact, the thing that Fabian and I found particularly surprising is that the local minimum problem is actually also hard. That is the thing that seems surprising to us. It's not so hard to believe that finding a global minimum is hard. It's the local minimum problem that's hard. That surprised us. And finally, there's a question of near vacua. We've talked about local minima. We've talked about global minima. And then you might ask, if you have some notion of a near vacuum, is that hard? So x star is an epsilon approximate local minimum of a continuous function if there's an open set containing that point such that f evaluated at that point is less than or equal to f of x plus epsilon times the distance for all x in n. This is the idea of a near vacuum, and you could define an associated problem near vacuum to basically find a point that phi star that is an epsilon vacuum. And there's an algorithm due to Vivacis that is in his book on complexity and optimization that finds this in polynomial time. So near vac, this problem near vac is in P. So somehow finding vacua is exponentially hard if P is not equal to NP, but finding near vacua is in P. Okay? So this is this question of finding vacua, near vacua, and near vacua. Question 4 is the following. What is the complexity of vacua in the string landscape? All I assumed in the last section is given V of phi find vacua and near vacua. Now we want to ask, we do something different in string theory. We actually determine v of phi, and many of us that do this, a lot of people in this room do this. We know that that's actually, at least intuitively, also hard, and we want to put some teeth on that. So, so the problem of finding vacua in string theory would be first compute v of phi, and then given v of phi, find the minima. So it's hard to find both stable and metastable vacua given v of phi. Computing v of phi is, of course, the subject of much string research, and so we want to ask, is it hard to compute v of phi? The goal is the following. Show that string contributions to v of phi require solving instances of NP-complete problems. The way that we did this is very elementary. We opened up, sort of the Bible of computational complexity from the late 70s, which has an appendix with like 100 pages of NP-complete problems. And then you just read through them, and you sort of go, does that sound like a problem that I do on a daily basis? And then you can have this map from their problems to our problems and realize that some of our problems are in fact instances of NP-complete problems. So I recommend this book of Gary and Johnson. It's very nice. So of course, there's the famous problem. I kid you, I'd never heard of this problem until I opened up this book, rural postman. Rural postman is the problem, and really this could be phrased in field theory also. Given a graph G and lengths L that label the edges, and a subset of edges, and some bound B, you want to ask, is there a closed loop in G such that that closed loop includes every single edge in the subset and has total length of no more than B? This problem is NP-complete in general, and also if edge lengths are set to 1, or if the graph is directed. But this is, in fact, what we do in equivalent gauge theory when we want to write down operators, gauge invariant operators, that couples some fixed subset of fields. You say, I want an operator that contains at least every field in this subset of possible fields, and it needs to be gauge invariant, and you bound the dimension by above by B. So finding gauge invariant operators that finds that include a fixed subset of fields subject to an upper bound on the operator dimension is in fact an instance of rural postman. There's another problem called integer programming, and in the interest of time, I'll be quick. This is basically the question of determining whether or not you have appropriate points of appropriate type in a box, or if an integral point satisfies a system of hyperplane constraints. Okay, where the latter cut out cones or polyhedra. But any time that we're, in many cases, counting lattice points of this type that satisfy hyperplane constraints is exactly the thing that we're doing when we do various cohomology calculations, for instance, in the case of line bundle cohomology on toric varieties, which is, of course, important for computing matter spectra or instanton zero modes or any other of a host of important problems in string theory. Quadratic DayaFantine is the problem of given a quadratic DayaFantine equation, does it have solution? The generic DayaFantine problem is undecidable, but any single quadratic DayaFantine equation is in fact decidable. What that means is, given a single quadratic DayaFantine equation, there is an algorithm which determines in finite time whether or not a solution exists. However, even in this decidable case of a single quadratic DayaFantine equation, it's known that the problem is NP-complete. And of course, you can imagine many cases in string theory where we have quadratic DayaFantine equations showing up. In my own work from years ago, this was in the context of Euclidean D3 7-brane instanton zero mode calculations, and it just can show up. Quadratic DayaFantines are hard. Okay. And in general, generic DayaFantines are undecidable, and for that and its implications for string theory, I refer you to our 2010 work. Question 5, and then we'll wrap up. What are potential complexity loopholes, and what does it mean for applying MLAI to landscapes? Loophole type number 1 is that complexity theory makes assumptions, break the assumptions, right? So it's about algorithms on a classical computer, assumption number 1, classical computer, that computes the problem. What compute means is it's an algorithm that definitively returns the correct result. That's what compute means here. So option number 1 is don't go classical. Of course, on quantum computers, so this famous factorization problem of given an integer, factorize it into its primes, this problem is in NP on a classical computer, but Shor in the mid-90s found a polynomial time algorithm for doing that on a quantum computer. That is a famous quantum result that gives you an exponential speedup due to going to a quantum computer. A caveat is that quantum speedup isn't automatic. Deneff and Douglas in their 2006 work have some nice citations along these lines, and it's been in the news more recently as well. So sometimes quantum computing can give you an exponential speed up, but in many cases, if your problem is order n, you'll get something on a quantum computer like order root n. And root n is not an exponential speed up. Another possibility is that you introduce some stochasticity. You have some probability in it. For instance, there's a problem that in cases with only strict saddle points, which is a special type of saddle point where the Hessian has positive and negative eigenvalues, you can escape those saddle points and find local minima in P. And this is relevant for machine learning, and it's a result of this work. The other way around it is not don't go classical, it's don't compute. If a 99% accuracy can break the assumption, but for some cases, for some problems that we care about, if we had some very, very high accuracy, but it took polynomial time instead of exponential, we would be willing to live with that. So, okay, accordingly, in both of these cases, there are extra complexity classes. Theoretical computer scientists don't stop at P and NP. There's other classes. BPP is bounded error probabilistic polynomial, and BQP is bounded error quantum polynomial. And these complexity classes allow for notions of error and also probabilistic and quantum algorithms, respectively. So how these things all fit together and which cases we have is still an open problem and something interesting to think about. The other loopholes are the following: special instances and reasonable n. Special instances, there can be instances that are in P. Nature sometimes utilizes them. For example, there's the idea of minimal frustration in protein folding. This is the mechanism by which proteins can fold in polynomial time, even though random proteins fold in exponential time. But that's the special instance idea. But on the other hand, people solve NP-complete problems every day. In real-world problems, including in theoretical physics, we often don't care about asymptotic n. You really only have to worry about exponential growth if n is so big in the problem that you care about that you're just killed by the exponential. An example of this is that there's a problem called knapsack 200 that if you put the literature together from Google Brain and also from the Arkani-Hamed-Dimopoulos-Kachru model, this is a cosmological constant problem in disguise, and they use reinforcement learning to solve knapsack 200 quickly. And 200 in that problem is exactly the number of moduli. And as string theorists, we said if you can solve a CC problem at 200 moduli, that's a regime that we think is pretty reasonable. We're not demanding that n is a million. We're demanding, be able to do something for n is a few hundred. Amazon solves traveling salesman problems every day in its warehouses. That's important because the number of items in your shopping cart usually only has order 10 items. This would be a much harder problem if you had 1 million items in your shopping cart. But again, it's about the cases for the problems that we actually care about. What is the relevant n? Okay, so each of these loopholes gives ways forward for computationally complex problems that we care about. As far as I can tell, there's no hard and fast rules, as we're used to with machine learning. And one should try the different potential loopholes and look for best results. Some techniques, for instance, reinforcement learning with stochasticity and the notion of epsilon greedy, can immediately have some of the loopholes built in. Okay, so let me summarize. We asked 5 questions, and I want to summarize each of them. Why should I care about computational complexity? The answer is that it's not rare. It arises quite readily in systems that we care about. There's the practical implication, which is one of the 2 obstacles that we run into in looking at large N landscapes in string theory. But there's also this potential physical implication that I didn't talk about much, that dynamics can be understood in some sense by complexity. Or at least that there can be hints about dynamics of systems by considering its complexity. What is computational complexity? It's a field that formalizes the relative difficulty of problems. And the key thing is that what we call hard problems are ones that take exponential time if p is not equal to np. Or have instances that take exponential time if p is not equal to np. That's the more precise statement. What is the complexity of vacua in landscape? So if I hand you a v of phi, finding critical points is hard. In the case that you have a critical point and a positive semi-definite Hessian, determining whether the critical point is a local minimum is hard. And near vacua, finding near vacua is in p. Of course, that is not the problem we have in string theory. We first have to determine v of phi. So what is the complexity of vacua in the string landscape, where you first have to determine what v of phi actually is? And determining the scalar potential involves solving many hard problems. What are potential complexity loopholes, and what does it mean for applying ML or AI to landscapes? On one hand, you can break assumptions by breaking the assumption that you're on a classical computer, or you can go and break the notion of having an exact computation. The other thing that you can do is you can use the nice instances, and nature does this in certain cases. You can have polynomial time instances even if the general problem is hard. Or you can point out, look, there's a particular value of n that I care about, and for some n, you might be willing to deal with exponentials. The punchline is that complexity does not equal to give up. The first time I read the complexity literature around 2010, this was the punchline that I took away, that complexity equals give up. And there are various loopholes and ways around it, and this is something that we're really going to have to deal with as we move forward with this field. So a final thought to conclude is that in some sense, well, not in some sense, I think it's true that most of the string landscape lives at large n, where n could be the number of moduli or various other things. Depending on your string construction, n can be different things. Most of the string landscape lives at large n, but complexity limits our ability to work in that regime. For instance, it limits our ability to make statistical predictions in that regime because it's so hard to work up at large n. In some sense, this motivates a concrete machine learning program. At various moderate n, what you could say is, I'm going to learn distributions for generating random effective field theories that match string observables. Getting it to match string observables is a learning problem. That's hard. And then you can study whether those distributions can be scaled up to large n. And if you can show that in any kind of robust way, you can imagine using machine-learned random EFTs to make predictions at large n. And this is what Cody's talk is about, in part. All right, thanks a lot.
Thank you very much, Tim. Are there more questions?